Good evening, everybody, and welcome to SecEd. Both people online, there don't seem to be many at the moment, but I'm sure there'll be tons in a minute. And quite a few in the studio here in the lecture theatre, so great big welcome. Apologies for any mix-up on the start time. It's a little bit of moving and updating websites and things. I think a flyer's probably got a bit confused. Thanks to Paul for highlighting that early today, and that's great. We decided to go for 6 o'clock because that's our normal meeting time. So, and if you are talk to anybody who's missed it, it's obviously recorded, and you better go back to it in the future. Just a few housekeeping rules. Fire alarms. If there's a fire alarm bell rings, there's exits at the back and here, and there will be people who will intercept us and guide us out of the building. But basically, you'll go out to the front of the building, down the steps that you came in, to your left, and left again into a street called Stories Gate. So that's what happens if you hear a fire alarm. There are other types of emergency, but we will only find out about those when somebody enters the room. I think that's about everything. Thank you on that. I think that's... Yeah, and another apology, just we've changed the speaker for tonight due to matters beyond our control. So thank you, Andreas, for joining us quickly with an excellent presentation that I'm looking forward to seeing. So basically tonight's subject, Andreas is going to talk to us about his post-processing of seismic action effects. Doesn't sound that thrilling, but I know there's lots of people that actually do this for their job, and they'll be thrilled tonight to actually hear a little bit more about it from an expert. So, just capturing what you already read on the synopsis, there's pre-processing, there's the solution, and then there's post-processing, and basically Andreas is going to concentrate on the post-processing because those first two stages are pretty automated. So that's the focus of tonight, and for me that's something I'm really looking forward to. Basically Andreas is going to draw on his 20 years experience and present an overview of what he's picked up over post-processing over that period. He'll refer to Eurocode 8 and ASC4 and discuss more sophisticated methods which have been deployed recently in UK nuclear new build sector. And then finally he'll identify some unresolved problems which we all have that even he hasn't solved. So let me tell you a little bit about Andreas. Turn over the page. Sorry about that. He's a chartered civil engineer working in Atkins SNCL, as I do, in Glasgow, not as I do, I'm in Epsom. His experience includes analysis and design of steel, reinforced concrete and composite steel, and concrete structures. I think he does composite concrete structures as well, don't you? Yeah. He's developed advanced methods for seismic analysis and authored several papers and presentations on various topics in earthquake engineering. He's provided consultancy service to the nuclear industry and other industries requiring expert advice concerning earthquake and blast protection. He's an annual guest lecturer at the Earthquake Engineering module in Heriot-Watt University. He's very personable, and I've thoroughly enjoyed working with Andreas over many years, learnt a lot. So, Andreas, if you'd like to introduce your subject for tonight, that would be lovely. Thank you.
Thank you, Ian. Thank you, Ian, for the kind introduction. Yes, so as Ian already pointed out, tonight's evening lecture has the very sexy title of Post-Processing of Seismic Action Effect. And as Ian perhaps also alluded to, you probably have to have some previous knowledge of earthquake engineering and seismic analysis to appreciate the meaning of the title. So I'm very pleased to see that some people have showed up for tonight's event. And Ian also touched a little bit on this slide here, which sets out the three main stages that are part of a seismic analysis. So first we do the pre-processing. That's where we build the model. We gather all the information we can about the structure in question, and we put together solid geometry, and then we mesh that solid geometry, and eventually we have a model that is ready for analysis. And then we do the solution, and at least the solution phase is very often highly automated. All we have to do is pick the appropriate solution procedure, which could either be a time history analysis, or it could be a response spectrum analysis, whatever we think is most appropriate. And then we press the button and out pops a solution in the best of scenarios. And then we face the task of post-processing. And in my experience, this is often the phase that people tend to underestimate, at least people with no prior experience in the field. After all, how hard can it be? All the results now are located in a large database within the computer, and all we have to do is take them out and process them. Well, it turns out that it's a lot harder than it seems, and that is the case in particular for seismic analysis. And I think less so is my thesis, less so for static analysis. So what is involved in, well, yeah, finally, if we then find something is not quite right in the post-processing stage, we might have to go back to the pre-processing stage and redo the whole analysis. But that's another topic. So what is post-processing then? Well, typically, what we aim to do with post-processing is to extract action effects. And what do I mean by action effects? Well, I mean anything that is an effect of the static or seismic actions that we have applied to the structure, such as displacements, internal forces, stresses, reactions, and so on. You might want to check acceptance criteria. So often we refer to code clauses, for example, Eurocodes, to check if the response of the structure, if those action effects that we've extracted are within the permissible limits. We might want to calculate reinforcement requirements for reinforced concrete structures. We might want to produce contour plots or other plots for our reports, extract data for validation purposes, and compute in-structure response spectra for qualification of plant and equipment. And in this presentation tonight, I'll focus on these two bullet points I've just highlighted on the screen, acceptance criteria and in-structure response spectra, as I think they're the most interesting. So in the first part of the presentation, I'm going to talk about how we go about checking those acceptance criteria. And then in the second part of the presentation, I will talk about in-structure response spectra. This whole presentation, incidentally, is based on a presentation I gave not long ago internally within Atkins, which was more like aimed to be a training seminar aimed at our younger and more junior engineers in the company. I've beefed it up a little bit, however, and I'm providing a few additional perspectives. So hopefully it'll be a more general interest for everyone in the audience. Okay, so acceptance criteria. Well, I've put here on the screen two very typical acceptance criteria, which you might recognize. The first one verifies that a bending moment, designed bending moment, is less than the bending moment resistance. And the second one verifies that the design shear force is less than the shear resistance. And I think both of these examples are taken from Eurocode 3. And each example really only considers one response parameter. In the first case, bending moment, and in the second case, shear force. However, we also have acceptance criteria that involve two or more response parameters or action effects. For example, the first one there on the screen is a check of combined torsion and shear. The second one applies to the forces within a shear stud. And the third one applies to the combined effects of axial force and biaxial bending moments in a steel column or steel beam. Now, all these acceptance criteria, they had something in common, and I'm going to draw out now what they have in common. And it will involve a little bit of math, but hopefully it won't be too taxing. So by R, I denote any action effects, any action effect. It could be actual force, it could be shear force, or it could be bending moment. Then for M, coincident action effects or response parameters, a generalized acceptance criterion is, and you can see on the screen, sort of tidy little mathematical equation. We have a function of our response parameters, and that function, generally speaking, has to be less than or equal to 1. And quite often by f, the function f, we understand the utilization ratio, or some people prefer to call it a utilization factor. So if our utilization ratio is less than 1, we're happy. If it exceeds 1, well, then we have a problem, and we may have to go back and re-examine the design or beef up the design if it's an existing structure. But what do I understand by coincident? Well, it has several meanings, and we're not always clear what we mean when we talk about coincident. It could be that the response parameters or action effects are coincident in time. They could be coincident in space, or they could even be coincident in load combination. So, for example, seismic actions occurring at the same time as other actions such as wind or snow. And it's quite easy to verify that it's conservative, and often a lot easier to check bounding non-coincident action effects as if they were coincident. But of course, it's not always in the interest of economy to do so, and we may find that we have problems if we go down this conservative route, and therefore it's of interest to know what we can do to reduce the conservatism in our approach. Now, consider now two action effects, R1, R2. As I said, they could be bending moments, it could be actual force, it could be stress, it could be displacement. And consider now that these two action effects are somehow acting at the same location, they're coincident in space, and they are interacting. Then for each section of interest, we can plot our acceptance criterion on this two-dimensional chart. And in this particular example, I've chosen a nice elliptical envelope, which would result from the equation you see on the bottom right-hand corner of the slide. But we can also have other envelopes that are not quite as nice as this elliptical shape. We can have envelopes that are not symmetric and indeed have a very irregular shape. But for the purpose of this presentation, I will only consider this elliptical envelope. Then I can plot my static design point on this chart, and that would just be a single point. And that is the result of self-weight, of wind, of live loads, etc. But I may have multiple static load combinations. I may have different values of static loads, snow, wind, different values of live loads or variable actions, as Eurocode calls them, and so on. So I can have multiple static load combinations. But for the purpose of this presentation, let's just for the time being assume that we only have one static design point, one load combination, static load combination to consider. Now, then what happens in an earthquake is everything is nice and still. The earthquake comes along and suddenly things begin to move. And I can represent this movement, this dynamic behavior, by letting my point wobble about, as just shown there. And that point now, during the earthquake, then in a time history analysis, will describe a path in my two-dimensional coordinate system And that path may, or may not, as it were, venture outside the envelope of my acceptance criterion. And if it does, we are, generally speaking, not happy. But if that path stays within the envelope, generally speaking, we are happy. Let's consider an example. A cantilever with a mass on top. And for argument's sake, let's say that this cantilever has the natural frequencies 3 Hertz in the horizontal directions and 20 Hertz in the vertical direction. It's not too important what these frequencies are. Let's say the base motion is as shown at the screen. On the screen, I have a 3-component base motion in the X, Y, and Z directions. And that is then, in a time history analysis, applied at the base of my cantilever. And what I note here is, when I inspect these motions, is that generally speaking, the positive value of each motion is of the same magnitude, same absolute value as the negative value, with one exception, of course, the one that's shown at the bottom for the AZ motion, where the negative value, the peak negative value, is greater than the peak positive value. However, that peak negative value you see there might as well have been positive in the general case. And that's an important point which we just need to remember for time being. I do my analysis. Let's say I'm interested in actual force and bending moments at the base of that cantilever. And I extract those action effects from the time history analysis. And again, I get time histories that have a different frequency content, because the motion, the input motion, has now been filtered through this system. What I can say then is, this is in principle all the information I need to check my bending moments and the actual force at the base of this cantilever. But I have to check each instant in time. And actually, for reasons I won't go into here, I also typically have to run multiple time histories. So when I do analysis of structures that have more degrees of freedom, larger models than the one you see here, this can become a quite data-intensive analysis. Aha, someone says, why do we bother running the full analysis in time? Why do we bother with all these points in time when we could just consider the peak action effects? And that is true. From time histories, we could just extract the peaks and dispense with the rest. And response spectrum analysis indeed gives us peak action effects, and so does equivalent static analysis. However, there are now 2 problems. One is that we lose the sign. And remember how I said earlier, we don't actually know if the peak excitation is positive or negative. In principle, it could be positive or negative. So the sign on the input motions is undetermined in principle. And so therefore the sign of the output, the action effects, is also undetermined. And moreover, we no longer know the simultaneous value of multiple action effects. So let's explore this in greater detail. First, we need some rules, though. And rule number 1 is that seismic action effects are fully reversible. As I said earlier, each action effect could be positive or negative. And therefore, we always have to check 2 fundamental load combinations: static plus seismic and static minus seismic. And I think that's a principle that is well known to everyone. Rule number 2, orthogonal seismic actions are uncorrelated. And that is actually a rule that is not, strictly speaking, 100% true. If you do analysis of lots of recorded earthquake motions, you will find that there is some correlation between different directions. But typically you can always determine two principal directions in the horizontal motions that are uncorrelated. But design codes such as Eurocode 8 and ASCE 4 will let us treat orthogonal horizontal actions, and indeed and also the vertical component, as being completely uncorrelated. And again, with the help of a little bit of math, we can understand this better. So if we let E of AD denote the peak action effect of earthquake excitation A in direction D, with D being X, Y, or Z. For example, in the case of the cantilever, the axial force was an effect of earthquake motion in the vertical direction, the X direction in this case. The moment about the Z-axis was an effect of excitation in the Y direction, and so on. Then those effects are also mutually uncorrelated. In other words, it's unlikely that the peak values occur at the same instant in time. Let's go back to those time histories that we extracted from the time history analysis of the cantilever. And we observed that at the time T1, when the peak value of the My moment occurred, the other two load effects or action effects were at 50% and 22% respectively. When the peak value of the MZ moment occurred, then the other two action effects were at 19% and 95%. And similar observation applies to the third moment in time, when the axial force is at its peak value. And if you look at these numbers a bit more closely, then we find that those coincident, when we get a peak action effect in one direction, then the other coincident action effects, they're typically sort of around 40% of their peak values. And if we did plenty of these analyses and we did statistical analysis, then maybe we would find that the true value is somewhere between 40 and 30% of coincidence, of correlation, if you like. And that leads to the so-called 140-40 rule, which in Eurocode 8 becomes the 130-30 rule. And that says that we need to consider three fundamental load combinations. First, we consider the action effects due to excitation in the X direction at 100%, and then we assume that the other two action effects are at 40%, and so on. And that can also be written like that. Hopefully, again, that's an equation that's familiar to everyone, most of the people in the room. We could also do a square root of the sum of the squares combination, where we simply take the peak action effect from each earthquake excitation. We square the values, we sum them up, and then we take the square root. And again, we have to consider plus or minus. And again, that rule should be familiar to everyone in the room. And that means in the case where we have one static design point, depending on which rule we follow, well, in each case, regardless of which rule we follow, we have 2 points we need to check. We need to consider static minus the seismic component and the static plus the seismic component, giving us 2 points on that line to check. So now let's turn to ASCE 4 and read more closely what it says. Well, it says, first of all, that the combination of spatial components, so that's the action effects due to excitation in different directions, must be combined or should be combined using the square root of the sum of the squares of the 140-40 rule. And we know how to do this already. For one response parameter, it was straightforward. Then ASCE 4 tells us when you have multiple response parameters, then the combined value of each response shall be calculated by square root of the sum of the squares, 140-40 rule, or the 140-40 rule, and then we'll get multiple m response parameters of interest. We'll get 2 to the power of m sets of response combinations. And what does that mean in practice? And I don't think that's crystal clear. And you have to read the commentary to ASCE 4 in quite a lot of detail to understand really what that means. But I'll try and explain it by looking at a few examples. Let's consider again the cantilever. We have 2 response parameters. We have bending moment about the y-axis and actual force in the vertical direction. Let's say the static values are 8 and -5. This is just an example, so the units don't really matter. We generate our 2-dimensional chart. We plot the static design point on that chart. And then we do the seismic analysis, and we find that the seismic bending moment is 15, the seismic actual force is 10, and they are due to excitation in the z direction and the x direction respectively. We do our 140-40 combinations. So first we do static plus 0.4 times E of AX and then plus 1 times E of AZ, and that gives us 0.1. Then we do the next combination, and that gives us 0.2 on the chart. And we keep going, considering all possible permutations of plus and minus and 0.4 and 1, until we've generated 8 points on this chart. And we can connect all those 8 points, and then we have what I would call a design envelope. So in principle, nx and my can assume all the values on that envelope, but in practice we are only interested in the vertices, the points that are numbered on the chart. I can also do what I would call a rectangular combination, which looks like a rectangle in 2-dimensional space, just by assuming that each action effect is at 100% and then doing the required sign combinations. So that is so far fairly straightforward. 140-40 rule, we have 8 vertices to check, and with the rectangular rule we have 4 vertices to check. And in this particular example, we may find that if we did the rectangular rule, we would have an exceedance. We would be outside the acceptance criterion. But if we did the 140-40 rule, we would be inside, so things would be lovely, as says there on the screen. But this is just an example. But what about the square root of the sum of the squares method for combining multiple response parameters mentioned by ASCE 4? Is that an ellipse, as shown there on the screen? Well, the answer is no. And I'm going to give you just one example to show you why it isn't. Consider now again the same cantilever, and consider shear force in the z direction and bending moment about the y direction. These 2 action effects are both due to excitation in the z direction. And let's say their values are 15 and 10. Again, we draw our interaction diagram. We put in the static design point. We do all our 140-40 combinations. In this case, we only have E of AZ to consider. The other 2, E of AX and E and AY, are both 0. So straight away, we can get rid of the ones that are clearly bounded by the others. We can get rid of 3, 4, 7, and 8. However, E of AZ has 2 components, both of which could have an uncorrelated sign in principle, unless we make the effort to investigate modal correlation. So that means we, in fact, still have 4 points to consider or to check. And that becomes our 140-40 envelope, and the rectangular envelope is coincident with that. But it doesn't take much effort to investigate the modes of a simple cantilever. And if we do that, we find that in every mode of response, My is always positive when Vz. The bending moment is always positive when the shear force is negative, and vice versa, which doesn't come really as a surprise. So we can get rid of 1 and 3 of those 140-40 combinations which are not physically viable, and that means that our 140-40 envelope now collapses to a line, and we only have 2 points to check. Now, if we were to draw the presumed square root of the squares, sum of the squares envelope on that chart, it would clearly be unconservative. So this little example shows what I don't intend to prove in this lecture, but instead just postulate, namely that the combination of multiple response parameters is inseparable from the combination of spatial components. In other words, you can't first do the combination of spatial components using one rule, say 140-40 or square roots of the sum of squares, and then subsequently apply another rule or even the same rule twice to the combination of spatial components. It's essentially one and the same operation. And the square root of the sum of the squares rule for combination of spatial components and multiple parameters, multiple response parameters, is the same method. In other words, the rectangular envelope is the square root of the sum of the squares rule. So that still should hopefully be basic, but I don't think it's crystal clear from ASCE 4. Then there is something, though, however, called the elliptical design envelope, which would allow us to draw an ellipse on this interaction diagram. And for more than 2 design parameters, if we have 3 or more interacting response parameters, this ellipse becomes a hyperellipse in m-dimensional space. And this method is described in at least 3 papers that I know of, which are given here on the screen. Hopefully, if you're interested, you can view the presentation in your own time. You're also welcome to contact me, and I can provide the references. Of those listed on the screen, I think 2 probably is the most comprehensive, and probably, for me at least, since I don't speak French very well, the easiest to understand. Let's consider another example, a cantilever shaped like the Greek letter gamma. Let's assume that this cantilever is subjected to 2 orthogonal motions in the vertical, one in the vertical direction and one in the horizontal direction. I have 3 load effects at the base of the cantilever: shear force, bending moment, and axial force. For now, I just ignore the static analysis. It's fairly straightforward. And I just do the seismic analysis, and I extract these load effects or action effects. And again, the units are not important. But it is a real example, by the way. And straight away, I noticed something funny or interesting, namely that excitation in the horizontal direction produces an axial force in the vertical direction. This I would not have picked up had I done an equivalent static analysis. So that's interesting. And I can then generate my design envelopes, and I'm not going to go through the math of doing this, but they're shown here on the screen. And I note that actually in this case, the 140-40 rule is no longer the most economical. It's slightly more conservative, it would appear, than the square root of the sum of the squares. And I've also shown there the elliptical design envelope, and it's clear that that is, first of all, bounded by the square root of the sum of the squares method, and it gives us considerable savings in that it cuts off the corners of the square root of the sum of the squares. So it's interesting. Definitely something that's worth pursuing if we find it difficult to justify our design or an existing structure using the square root of the sum of the squares, or 140/40. However, a little bit of math, I won't have much more in the presentation, I promise, but we learned then that the number of vertices on the design envelopes relate to the number of response parameters, m, according to these equations here. And for the ellipse principles, we have an infinite number of points to check, but in practice it can be reduced to a finite number, of course. And for more than 3 coincident action effects, we generate quite a few points. And when it then comes to assessing those points, then really we have rarely any option but to try and do it, try to automate the task, get a computer to do it. In other words, write a script that can do the work for us. Let's now consider the case where we have 4 static lode combinations, and each of those static lode combinations is associated with an ellipse. And we can see that the envelope of those ellipses is a fairly complex envelope of irregular shape. It's no longer described by a neat mathematical equation. How do we determine the outcrossings? How do we determine when that envelope is no longer bounded by the acceptance criterion? And how do we determine maximum utilization ratio? Well, those becomes questions that can only be answered through fairly complex math. And I'll come back to those math in a second. But just summing up this discussion, some pros and cons of these methods. Well, we've seen that the rectangular envelope is simple and conservative. We need to put a little bit more effort into it if we apply the 140/40 rule. But it can lead to savings, especially when each response parameter is caused by excitation in a different direction. The elliptical envelope requires significant effort. And indeed, you need to write your own scripts if you are going to do it. You cannot rely on existing software such as Abacus or ANSYS to do it for you. But it can lead to substantial savings in design. However, but due to the complex math that I've just tried to outline for you, it's debatable if the method is really any simpler than the time history analysis we started out with. The scripts required to evaluate the required load combinations become highly complex, leading to what I would call black box conditions. So if we have the 2 methods here, time history analysis and response spectrum analysis, at the end of the day, which one is more transparent then? Well, I would argue that it's time history analysis, unless, especially if we go down the route of applying elliptical design envelopes to response spectrum analysis. And that leads us back to the, by now, rather sort of a mature question that has been posed several times, namely, is it time then to retire the response spectrum analysis method and just do time history analysis, if after all, at the end of the day, that is simpler? So I'll leave that question with you. And then I'll go on to talk about the second topic of tonight, which is in-structure response spectra. And here I don't propose to go through sort of the same fundamentals as I did with the post-processing of multiple action effects. I'm going to take sort of a more general view in this second part of the presentation. Now, but just to summarize, just to refresh our memories, as it were, what is an in-structure response spectrum? Well, consider, for example, we have a structure And at the base of that structure, we have some input motion and earthquake excitation. The structure responds, it vibrates, and then we can extract the motion within the structure at a point where we may have some equipment, for example, and the equipment may or may not be modeled explicitly. In most cases, it won't be modeled explicitly. In most cases, we'll just have some additional mass that allows for the mass of the equipment. But that in-structure motion, the yellow line there, we can then turn that into an in-structure response spectrum. And then we can take that in-structure response spectrum and hand it over to the designers or the suppliers of that equipment and say, here you go, this is what this equipment has to withstand to fulfill its functions at this particular point in the structure. All well and good. And in my time in the nuclear industry, I've seen multiple in-structure response spectra, and they're presented, they typically look like the ones you see on the screen. Just a few examples from from a great number of plots I've seen over the years. And now our computing power has increased dramatically. We are even able to compute in-structure response spectra at every single node, even for very large structures, large models, such as the one you see on the screen. And when we are able to compute in-structure response spectra at every single node, then we are also able to produce contour plots. And we can choose what we want to show on the contour plot. Very often what is of interest is the peak spectral acceleration or the zero period acceleration, which are commonly shown on contour plots. And that gives us sort of a heat map of the response to the structure. And it perhaps tells us where we can put equipment and where we perhaps should rather avoid putting equipment. But there are some challenges, admittedly. First of all, our in-structure response spectra are sensitive to modeling. And I'll show an example later on, but this is what we find. If we tweak the model a little bit, often we can get quite dramatically different results. They're sensitive to damping, and they are also sensitive to coupling between primary structure and secondary equipment at tuned frequencies. By tuned frequencies, I'll explain what I mean later on. And that means, as I hope to show in the remainder of this presentation, this means that in-structure response spectra typically have a much lower annual probability of exceedance than the free field input motion. In other words, they are much more conservative. Now, model sensitivity. Here's an example, a real example from a real site somewhere in the UK, the details of which I cannot divulge in this presentation, but nevertheless, this facility has been analyzed twice, first in around 1990 and secondly around 2012. And in 1990, obviously computer power wasn't as advanced as it was today, so the analysts quite sensibly chose to construct a stick model. And this stick model had, from memory, and I'm pretty sure this is correct, 54 degrees of freedom in total. Fast forward to 2012, and computing power has advanced tremendously. We are now able to build large, detailed models using shell elements. And this model on the right from 2012 probably has hundreds of thousands of degrees of freedom. Vastly more sophisticated model. And what we see then, when we compare the in-structure response spectra predicted by the two models on the same chart, is that they look completely different. So the 1990 model had a dominant mode around 20 Hertz, which produced a very significant peak, as you can see there, at that frequency. The 2012 model had no such dominant mode. It had a multiple of local modes, but no dominant overall sway mode. And the peak you see on the chart is in fact largely due to soil structure interaction, not due to structural response at this particular point in the building. So the two are vastly different. And that leads one to speculate, well, what would happen if we try to analyze this structure again here in 2022, using perhaps even more detail, even more refined modeling? Would we get a third answer that's completely different? At what point do we converge to a single answer? At which point do we gain confidence in our model to predict the right answer for in-structure response spectra? It should be noted that between 1990 and 2012, no new physical information had come to light. These two models were built on the same ground investigation, the same geotechnical parameters, the same knowledge we have today even of the stiffness of reinforced concrete and so on. Then there's the whole question of decoupling. And perhaps the chart that is now on the screen will be familiar to many of you. Again, it comes from ASCE 4, and it defines ASCE 4's criteria for dynamic coupling or dynamic decoupling. When can you assume that secondary equipment is decoupled from the response of the primary structure? When can you analyze the two separately, and when do you need to consider them together? And on the x-axis, we have the mass ratio, and on the vertical axis, the y-axis, we have the frequency ratio. However, this just shows the error we would. This chart here is just based on achieving less than 10% error in frequency, in natural frequency. But actually, we're not that interested in natural frequency at the end of the day. We're interested in response. We're interested in stress and things like that. So actually, this chart here, I feel, can be a little bit misleading. Perhaps it would be more rational to use a chart that shows another parameter of response. So here's one I picked out from a paper from 1986. It shows the error in root mean square acceleration of the secondary system. And root mean square acceleration is a very good indicator of peak acceleration in that secondary system in the equipment. And peak acceleration, again, is a very good indicator of the forces in the secondary system. So this is, I feel, a more meaningful chart to use. But you can see there are similarities between the two. They're not too different after all. But what is worth noting here is that the unconservative error is limited to a very small portion of that chart. Everywhere else on that chart will be the error we do in predicting root mean square acceleration would be conservative if we use the decoupled approach that is implicit in the production of in-structure response spectra. So mostly we're committing a conservative error, which perhaps is reassuring. But let's now again also consider this line here, which corresponds to a frequency ratio of 1. This is of a particular interest in the context of in-structure response spectra, because at a frequency ratio of 1, this is exactly where the equipment is tuned to the frequency of the primary structure, and this is where we generate the peaks in our in-structure response spectra. Always the peaks in in-structure response spectra occurs when the secondary system is assumed to be perfectly tuned with the frequencies of the primary structure. So that's of particular interest. Let's go back to these two charts, and let's examine more closely the error that occurs at a frequency ratio of unity on the right-hand chart. And we see that for a mass ratio of less than 0.003, so less than 0.3%, we commit 10% error. For a mass ratio of 0.006, the error is 25%. For less than 2% mass ratio, the error is 50%. And for less than 4% mass ratio, 0.04, the error is 100%, a whooping error. But if you go back to the chart on the left-hand side, that chart would tell us to happily ignore any coupling between primary structure and secondary equipment. So the chart on the left would happily permit us to introduce 100% error, in other words, in our in-structure response spectra. Let's consider a real example. This is from a real facility somewhere in the UK. Again, I cannot go into the details, but it's a real example. A slab that has the dimensions shown on the screen there. The total mass of the slab is some 125 ton, but really if we look at the modal mass, it's only about 80 ton. This is the heat map, or the contour map of peak spectral acceleration for that particular slab. And we see that the acceleration has a quite significant, it varies quite significantly from 0.7 g at the edges to 9 g at the center of the slab. Let's look at the in-structure response spectra at the center of the slab. And we see that peak at now of 9 g, which occurs at the tuned frequency I mentioned earlier. And that's exactly because the slab has a natural frequency. It has sort of a bounce trampoline mode, if you like, at it's around 20 to 30 hertz, I think. Okay, that's quite a lot, 9G. I have to admit I didn't quite believe that when I saw it in the first case, but it is mathematically correct. Whereas the input spectrum, the free field input spectrum that is applied at the base of this model only has a peak spectral acceleration of 0.7 g. So in other words, we're amplifying the input motion by a factor of 14 in this case, which is quite remarkable. Let's now actually try and put that secondary system at the center of the slab, and let's model it explicitly. So I've added this secondary system explicitly to the model, stuck it in a little single degree of freedom oscillator with a mass of 0.8 tons, 800 kilograms, with a corresponding to a mass ratio of 1%. Normally we would wave this away and say, oh, the two are uncoupled. Surely that can't make any difference. But it did. So when I ran the analysis with this secondary system in place, the in-structure peak spectral acceleration reduced from 9.1 g to 5.7 g, a reduction of nearly 40%, which is actually totally in line with the chart I showed you earlier. It was to be expected, actually. So we've seen that in-structure response spectra tend to overestimate the spectral acceleration at tuned frequencies. Often these in-structure response spectra, they're calculated as envelopes of multiple parametric variations. So, for example, lower bound best estimate and upper bound soil parameters. And each parametric variation has a finite probability of being true. They're often envelopes over large areas, so typically for that slab in question, we would just produce the envelope for the whole slab, and we would assign all the equipment to that envelope, even if the envelope is located around the edges of the slab, where the spectral acceleration was a lot lower. The in-structure response spectra are often peak broadened, and sometimes if you have multiple peaks, the valleys between these peaks are filled in. Damping is quite often underestimated, especially if you have these high accelerations. It seems incredible that we only have 2%, 4% damping in a structure like that. and often we ignore radiation damping through the soil. So all this means, and this is my key takeaway tonight, is that in-structure response spectra have a much lower probability of exceedance than the input motion. It's fine, it's conservative, but it can cause a lot of problems in the qualification of plant and equipment. We often find it very difficult when we're presented with an in-structure response spectrum that has a peak acceleration of 9g to qualify anything. And we find it difficult to find a shaker table that can produce these high accelerations. Some final thoughts before I finish for tonight. We've seen that advanced scripts are required for post-processing. So nowadays, engineers, I would say they need to come out of university with skills in programming, and preferably some experience with using a programming language such as Python, if they want to have a career in this particular line of business. However, engineering consultancies are often not set up to be software developers. Actually, if I'm honest, I think many consultancies, at least the ones I know of, are not very good at it, to be honest. Things like version control, checking, documentation often seems to get lost. And if an employee leaves that had written a script, often that script becomes unusable because we have nobody to maintain the script. It's never handed over. Seismic analysis is characterized by a dichotomy between simplicity and complexity, and conservatism and economy. However, whichever route is taken, engineers should not take leave of common sense. They should be able to interrogate models and explain the response in simple terms. Unfortunately, sometimes when I've pressed engineers to do that, they flatly refuse. They believe the scripts have been validated, but have the validation really checked every route through that script? Have they really been subject to really rigorous software testing? And why is it that we see these very high accelerations sometimes in the in-structure response spectra? Are they really realistic? And they should be able to perform hand calculations to check order of magnitude. Should the response spectrum method be retired? That's the question I posed earlier in the presentation, and I'm sure we'll still debate that in 5 years to come. And finally, I think that the industry should address the conservatism in in-structure response spectra through research and development. There are methods out there that can fairly easily account for the presence of light equipment in structures. So should we make a concerted effort to implement those methods? What would it mean in terms of the number of the data we generate? How can we present that data in a reasonable manner so that it doesn't overwhelm people? And I think with that, I'll finish tonight's presentation and just thank you all for attending. Thank you to people who showed up in the theater, and thank you to people who attended online. Thank you. And I'll invite questions.
Thank you very much, Andreas. That was delightful. Thank you very much. It's great. However, however simple these things are, you always find out more every time somebody presents these things. So thank you very much. I think you also started producing a little bit of information on the background to tune mass dampers in terms of the 1% mass having such an effect.
Yeah.
Even though it wasn't modelled as damped, it was just there as a mass in just the right place. So insight all the way around. So thank you.
Thank you, Ian.
Before we start, if we could just hand the microphones around. Andy, would you assist slightly? I think we probably only need one. great. So, anybody like to ask Andreas some questions on that wonderful topic? If you could say your name and affiliation, that would be appreciated.
Hi, Guillermo Aldama from Jacobs. Thank you very much, Andreas, for the presentation. I think it's really, really good. And there's a lot of points that you raised that triggered a lot of questions. I have so many things to ask you and discuss with you, but I think I'm going to keep it just down to 2 points. One is going to be a comment, the other is going to be more a kind of a question. The first one that is the comment is, I think I particularly like your last slide about doing hand calculations, checking the basics of the analysis that you're doing. I always try to raise the point of the use and abuse of numerical methods. Somehow there is the belief because you're using complex numerical methods, you are going to get more reliable results, which is not always the case. And I will say even that is not even often the case, because many times we have to work with limited data to develop the constitutive models that go into the numerical analysis. So I don't work on on the structural side of things. I look more at part of the geotechnical issues. So when they try to use complex numerical modelings, and then basically the GI is based on just SPT, and all the parameters are derived from that single test. So, and sometimes people are very keen on doing complex numerical analysis, but the data that they have is just very limited. So, and also the design process should go from doing simple back of the envelope calculations to get you a sense of the order of magnitudes that you are you are looking at, and then refine your models and try to go to more complex models, to most complex numerical analysis. I think that particularly, I like it how you highlighted, and that was kind of my comment. The second is comment/question is, you said earlier in the presentation, and then at the end was kind of your conclusion, that the in-structure response spectra have lower annual probabilities of exceedance or frequency of exceedance than the input motions. I kind of disagree a little bit on that, just on the term of use probabilities, because for what I understand, what you were presenting is that everything is based on those are deterministic analysis. Even if you perform multiple type of analysis, at the end of the day, those are deterministic. So, and I have seen that argument being used often to try to defend the design basis, because the accelerations, you have higher amplitudes on the spectral accelerations, that means I have lower probabilities of exceedance. If the integration of the response to the response to the structure in this case is not integrated in a probabilistic manner into the results of the PSHA. So I'm not saying that they are not conservative. I'm just saying that probably just saying that they have lower probability of exceedance might be not strictly correct, unless you think otherwise.
Thank you for the comment, and thank you for your insight. Yes, I would agree. I mean, you're right. As soon as we get the input spectrum, which often nowadays has been derived on a probabilistic basis from you guys, the seismologists and the engineering seismologists, from that point onwards, often things are done deterministically. So yes, does it make sense then to talk about probability of exceedance then for a parameter that has been determined or calculated on a deterministic basis? Perhaps it doesn't, but I think ultimately a lot of the whole safety case that we operate with is fundamentally rooted in probabilistic terms, in that we are required to show that we're required to show that we're in the alarm region, or we are in the broadly tolerable region of the response, and that those regions are sort of defined in probabilistic terms, in terms of frequency or probability. So ultimately, it sort of falls back on us to say, perhaps as engineers, well, at least we've not significantly reduced or increased rather the probability of exceedance in the response parameters, the action effects that we predict. At least the action effects have the same probability, at least, as that of the input motion. Yeah, I'm not sure where I'm going with this response, but it's certainly food for thought. So just thank you, Guillermo.
Perhaps a debate for later.
Yeah.
Well, thank you very much. That's great. Any more questions from here?
I'll have one here.
Yeah, great.
Andy Mayer from Jacobs. I'm going to go straight to try and attempt to answer the question that you posed about the response spectrum method. One of the things is, I'm at the end of my career rather than the beginning, and one of the things that I have noticed, that we all have, I guess, is the increase in computing power in my lifetime has been absolutely phenomenal. But what I think that has led to is complexity in numerical modelling for the sake of complexity. Because the computer can do it, people are doing it now rather than they need to do it. And you showed an example of a heat map of SRS, which, I don't know, maybe even 10 years ago would have been unheard of. It's quite unbelievable we can do that. But in that complexity lies a problem, because even with simple time history analysis, 2D models, for example, I often find it difficult to know what is really going on in the structure. And the thing that appeals to me about the response spectrum method is being able to visualize mode shapes and mass participation associated with those mode shapes. If you can get those two things in your head, if the engineer can see the mode shape and the mass participation for each of those modes, I think he or she is a long way to understanding how the structure performs. So my view is, no, it's not time to bin it. If anything, we need to hold on to it. It might be a validation tool on the way to a time history analysis, but I would like to, you've asked the question, I would like to understand your views.
I fully agree. It should never be fully binned. It should always be there, if nothing else, as a validation tool. And we should always do a modal analysis, I would agree. And we should always look at the modes. But for very large models, some of which I showed on the screen tonight, they have thousands of modes. And what I feel would be valuable for engineers to be able to do is actually find those modes that are important in terms of the local response. So this particular slab I showed, that had its first natural frequency, the main dominant mode of that slab occurred in mode number 1470. And there's no way you can find that mode just by flicking through the results one by one, looking for that mode. You need to be able to go in and be able to interrogate the model and find a way to find the local modes that are of importance. And once you've done that, yes, you can then use that insight, and I feel that's very important. Use that insight to understand the local response and why is it we're seeing this tremendous peak at 30 hertz, and what is driving that. And exactly that's why, because we have a mode of that frequency. So I would agree that the response spectrum analysis is appealing and still of value from that point of view, and certainly should not be entirely bent. I hope I didn't give the impression that I was sort of wholly in favor of doing that, of binning the response spectrum method, because that's not the case, no.
Yeah, I think I'd like to add as well, Andreas, in our company, we're still very strong on hand analysis, very strong on simple models, get the understanding of the structure, and then advance. What's tragic is people going straight to complex FE models, and then you've got no benchmark. You don't know where you are. Equally, complex models can throw up modes that the simpler ones can't, as you very helpfully explained. My own personal opinion, and it's very much a personal opinion, is there's more to offer by having a reliably ductile detailed structure to respond to variability than the complexities of the soil. I'm not saying don't understand the soil. I think you've got to advance on every frontier, but I think engineers sometimes Guillermo's comment about not respecting the soil or the variability of the soil, I think equally the structure can be made so much more robust than its intricate complexities by just actually making sure it's been detailed in a way that it can accommodate misuse by whatever force functions are on it, be it impact, seismic or whatever. So, very interesting subject. Thank you very much.
I think, Ian, that point that you're making is reinforced if you simply look at photos from earthquakes that have occurred, structures that have collapsed and such, like the EFIT missions and all the rest of it. The amount of times you see things that have failed badly simply because of poor detailing is unbelievable. So your point is very well made.
Absolutely, and the ones that survived, you think, well, how on earth that survived? It's probably because it was very flexible or very simple in its concept, but well detailed or well constructed. Yeah, thank you. Any more questions here? Otherwise, I've got one online. Okay, we'll go to the one online. I'm going to read this because I don't fully. I think it's off the topic, so if you don't want to answer this, that's fine. But it's from a gentleman in India. What is the threshold to permit the use of design spectrum from the codes, and when is the site-specific spectrum necessary to be referenced? I really think that's off tonight's topic personally, but it's a question that's been asked. I think it's fair to raise it. I think probably as a group, as SecEd, we're probably more interested in people always looking at site-specific characteristics, both the actual earthquake, but also the site characteristics, site geology, seismology of the area, seismicity of the area. I think it's a very complex subject. It's probably not one for tonight, but if you have anything to add.
Yeah, well, I'm wondering whether it refers to when we would use site-specific input spectra and when can we just use the generic ones from code. And certainly when it comes to high hazard facilities, such as nuclear facilities, we would very often use site-specific input spectra that have been derived based on a site-specific study, whereas for lower consequence structures, as Eurocode calls them, we would quite happily just use a generic design spectrum from the code.
Yeah. Okay.
I hope that answers his question.
Yeah.
His or her question.
Now this is a phenomenally long one now. This is from Kostas Geopoulos, so we all know him. Hi Ian, dear Andreas, a very thought-provoking presentation. When I was working on the design of the Trident submarine refitting facility in Rosyth in the late 80s, I think there's some connection with your work, isn't there? Not in the late 80s, but more recently. It wasn't actually built. I used to say to friends in Edinburgh that the safest place to be if an earthquake hits Edinburgh is next to the reactor of the Trident. Over 30 years later, are we still being extremely conservative with the design of our nuclear facilities? ? And with regard to RSA and SRSS, I believe that the second generation of Eurocode 8 to replace the national codes in 2028 still recommends them as a way forward for non-nuclear facilities. So time history analysis is really far away from reality. So I think that's just a perspective which is very valuable from Kostas.
Yeah, we're still being very conservative. I mean, it has occurred to me that should a design basis earthquake hit Glasgow, for instance, instead of one of the nearby nuclear sites, what would be the damage and what would be the cost in terms of not just the financial cost but also in terms of human lives, since no building in Glasgow is designed to resist earthquakes. And would it be, I mean, we take great care, obviously, because with nuclear facilities, because they contain such hazardous material, but are we being too conservative? Oh, it's a tough question to answer. Was there a second part of the question?
I think I was just giving a perspective.
Okay,
so
but there's a perspective, yes.
Yeah. Unless we've got another one here, I've got another one online. No? Okay.
Can I comment on that one? Just a comment on that, like, whether we are being conservative or not. At the end of the day, I think all these seismic designs, particularly for high-risk facilities, is very difficult to say whether we are being conservative or not. I think it's all about risk, and we have to manage and control risk. Somehow the regulator has defined what are the acceptable risk levels based on what we were discussing before, that are the annual probabilities of a certain threshold ground motion being exceeded. So at the moment, because we are not strictly answering that question for some cases, like in this case, the structural response, there could be a perception that we are being conservative, but until we are actually able to confirm that in a fully probabilistic manner, probably we won't have the answer. We don't know how conservative we are. Somehow I feel that it's just more a perception that we are being conservative rather than having the strong arguments to support that statement.
Thanks, Guillermo. Anything to add to that? Or?
Yeah, I do know that some studies have been done using fragility functions, for instance, to try and determine what is the probability of collapse given if an earthquake of a certain probability were to occur. So you find that 1 in 10,000 year earthquake occurs with a probability of 10 to the minus 4 being exceeded. Then the probability of collapse is down at 10 to the minus 5 or 10 to the minus 6, which is roughly where I think the regulator wants us to be, based on studies that have been done into people's perception of risk and what it constitutes tolerable risk in society. Studies that were done, I think, back in the 1980s and 1990s. So, yeah, we don't know, of course, the specific probability of collapse or even the probability of an adverse consequence, because collapse does not necessarily mean that there is an adverse consequence in terms of a radiological consequence, but we don't know exactly what those probabilities are, what those risks are for in each case, but we probably have a good sort of intuitive feeling that we're talking at least a magnitude lower than the 10 to the minus 4, that is the probability of the exceedance of input motion.
Right, thanks, Andreas, and thanks again, Guillermo.
Ian, can I make a comment on this thing about are we over designing for earthquakes or being too conservative with our high hazard facilities? I guess, I mean, there's a number of people in this room and there's people online that have spent their life working in these industries and will have a view on this, right? And I might have my view. But I don't think any of us can definitively answer the question, are we being over-conservative or not? But my observation would be, having spent a large part of my career working in this field, is not so much are we being over-conservative, but are we not a bit pedantic at times, and do we not get sucked into the problem too much, rather than doing what you suggested, the good detailing type thing? And what my observation would be that when I look back in many of the facilities that I've been involved in, working with multiple clients, as I've seen a phenomenal amount of money and time spent getting nowhere with these things, because of the complexity of the subject matter that we're dealing with, and Andreas showed some of that tonight. It is fertile ground for peer reviewers, regulators, whoever it is that's going to come along and look at this and ask question upon question upon question, and we get nowhere. So I think the better thing to do if we're going to improve value for money and such like is to be more pragmatic with these things and not start looking into the detail all the time. I can live with the conservatism. It's the management and everything that goes with the process, I think, is the thing that we really need to think about.
Yeah, very, very much so. That's a great point. Thanks, Andy. I think also the, how can I put it, with sustainability issues and carbon and things like that, there's going to be more pressure to look at that conservatism, and the context you've just given means why we might have to be very, very careful. my own observation is that there's a lovely figure in Eurocode 2, the current one. I think it's being dropped or it's being presented in a different way. But what it does show quite clearly, it's showing the hinge rotation capability of a section of concrete, slab or a beam, in terms of moment hinge rotation, as depending on the compression depth. So when you've got a low level of tension reinforcement and a low compression depth, you've got massive plastic rotation capability. But we in our structures absolutely cram the steel in like there's no tomorrow. And if you look at the rotational capability, it's incredibly low. So for me, my mantra is very much keep it simple, keep it ductile, but in that context say, well, where can that ductility be realised in our whole structure? It's probably a fraction of 1%, where, if you look at a slab, it's not going to go plastic everywhere. There's Hillerberg helped us out on that. He showed the areas that were going to go plastic, and when it goes plastic, what is the coexistent shear? So I really don't think we reinforce structures very well. We reinforce them to the code and to the analysis, and we do it in the perspective that you've just described, Andy. But I'm not quite sure how far we've got. It's just an observation. Any more questions if you want to move on to a different area of tonight? No? I've got one more. I think we're good for a few more minutes. This is from Omar Lagrouche. Don't know where he is. Oh, here at what university, so local. Time history analysis allows accounting for geometrical and material non-linearities. It can do, I don't think usually it does for what we do. For example, plasticity. So that's the statement. Can the elliptical envelope approach account for the effects of such parameters? So I think he's talking about the plasticity. Is it beneficial to run both approaches for final designs? For me, that's a little bit looking for precision in something, but does that make sense to you?
Yeah, it does. It does, I suppose, to some extent. Yeah, so everything I've covered tonight is broadly based on the assumption of linear elastic behavior. So things get interesting, of course, when you start to consider nonlinear behavior, such as geometric nonlinearity or plasticity. I suppose if you were to do a trial time history analysis in the first place, one of the benefits of that is that you don't have to go into the whole elliptical method computations. You just follow that path I showed on the screen earlier. You check each moment in time, and you only have one point to check. You don't have an envelope in time. It's only when you start then to extract from time histories the peak action effects, and you discard the information about their coincidence in time, then that's when you would have to probably consider using an elliptical combination method. Is that then, could that be used for nonlinear models? And what happens when we start to use an inelastic design spectrum in response spectrum analysis? I have to admit those are questions I haven't given much thought to. So,
yeah, because I think that for me the plots, when you get plasticity, your envelope moves, but if it's an acceptable plasticity, it doesn't degrade in strength. So you've got just an envelope somewhere else.
Yeah.
So it's really complicated. But it's a good question.
It's a good question. Yes,
yeah,
I think so too.
Yeah. I think also it's very important that you understand your material, particularly in reinforced concrete, but the same in structural steel. If you didn't have a strain hardening material, you wouldn't get plasticity. You just get very local plasticity. You wouldn't get member plasticity. So again, I think understanding all the characteristics and the rate of strain hardening is quite important. You don't want it too steep, and you don't want it non-existent. You need a degree of strain hardening, and it needs to be proportionate to make sure the plasticity disperses along the member. So, right. Well, I don't think we've got any more questions there online, and no more in the audience.
I've got one, but it's a cheeky one because it's a bit unfair on Andreas. But I'm going to ask it anyway because I'd like to know the answer. And if he can't answer it, maybe somebody else in the room or online can. Early in your presentation, you showed an example of combinations of orthogonal forces. and I think he said that the average of the peaks came out at 37% or something, and he said that's the basis of the 140-40 rule, which we'll all be familiar with. And I don't know where the 140-40 rule started, but it was there when I started my career in this. And then, as you pointed out, along comes Euro Code 8 and it becomes 130-30. Do you know why?
I don't know. I don't, to be honest.
Does anyone know?
Can I say I did know why? Because I asked, probably with similar careers, when I started, I wanted to know the answer. So I looked in, it was one of the ASC, probably ASC 4 actually, as it was, in the references. And I got all the references. And they're in my garage. I'm emptying my garage of all the rubbish and junk now. And I'm hoping to come across them. They're a little collection of about 6 papers. And they do actually give you the background to those. And it's quite interesting because they're quite diverse, and there's comments on the papers about other papers. So if I find them, maybe that should be something I give to SecEd, but I haven't found them yet.
I look forward to that.
I think Paul has a comment to make.
Yeah.
I just wanted to respond to the comment about the 140-40 rule. I was going to talk to Andreas about it in the bar later on.
Oh, I'll hear it now. Paul.
When I started working, I'm probably one of the older one here, for the nuclear industry we used 30-30 was the rule.
That's it.
As a Eurocode 8. And then somebody pointed out that if responses were of a similar order of magnitude, 130-30 may not be conservative enough. If they're of equal magnitude and you do the SRSS, you get a root 2 factor.
That's right.
And root 2 is 1.41, so that was rounded off to 1.4. And that's what I understand is the origin of the 140-40.
Oh, right.
The process that Andreas put forward is very interesting. It's another way of looking at it. But I'd say I always thought it came from a simplification of the SRSS with components of near equal magnitude.
Yeah, I think I said earlier that the 40, the value 40 had been determined on a statistical basis based on analysis of many time histories occurring at the same time, but I'm actually not sure that statistical analysis has ever been done. Well, I know that there is a very good reason for the square root of the sum of the squares method, which is based in probabilistic analysis of uncorrelated motions.
I'm sure in the 70s when I first came across the 140-40 rule, I don't think the computing power was available to do sort of detailed statistical analysis of all these things. I think it does come from just this simplification of the SRSS with 2 equal components.
Thank you, Paul. I think in the commentary in ASC4 it's got the background to the SRSS. Again, I can't remember, but I remember there's quite a few pages on it, and that's got the probabilistic background. Excuse me. Right, well, just before I thank Andreas, just hang around for a few minutes. I want to just tell you what's on the programme for our future meetings. But Andreas, to start with, the things like many thanks, excellent topic. There's a lot of people very thoroughly enjoyed this evening, so thank you very much for that. You brought an excellent topic to life. It's been a lovely debate. That's what we're here for. It's really, really good, so thank you for that. And then on behalf of everyone here and everyone online, thank you for an excellent evening. Cheers, Andreas.
Thank you. Thank you very much.
Right, just before you go, just very quickly, regular last Wednesday of the month, except for tonight, meetings. Look out for those on the SecEd website. There'll be the next year's meetings starting January next year. Keep a lookout for that. Real rosy stuff to look forward to next year. We've got the 18th Mallet Mill lecture in May, so look out for that. That's Professor Alan Baker, civil engineer. He's got a vast breadth of knowledge, and to have him talking about the things he wants to talk, he's going to talk to us about the interrelationship between practice, standardisation and innovation in earthquake engineering. So a lot of the people, the younger people particularly here, you'll be thinking of all these innovative ideas to apply, but he's actually lived through the standardisation and then the looking at that innovation, how we can apply it, and then looking at practice that doesn't probably follow the standardisation or the standards. So I think that'll be a thoroughly enjoyable subject. There's more on it on the website, a proper abstract, and even better, I think, because it's a bigger group, SecEd next year. We've got the SecEd conference. That's in September next year, so keep an eye out for that. That's coming together very nicely. There'll be an excellent range of topics to study there, so look out for that. So look out all the last Wednesday of the month meetings, Mallet Mill lecture in May, and then the conference in September. So exciting times ahead. So thank you again, Andreas. Thank you everyone for coming. Thank you everybody online, and we look forward to getting together in the new year. Okay, good night.
Good night.